Hello, my name is Richard van Rooij, and today I want to talk about the Mandelbrot set. The Mandelbrot set is a very famous example of complex dynamics where a simple function, namely f of c equals z squared plus c, gives rise to an amazing complex infinite cosmos. A point here in the complex plane is considered to be part of the Mandelbrot if the absolute value of z stays below 2 after recursively applying this function. So, for any point c here in the complex plane, it is considered to be part of the Mandelbrot set if, after recursively iterating this function, z, the absolute value of z, stays below 2. Let's give an example, an easy one, here on the real axis. 0, which we can see is part of the Mandelbrot set. F, c is 0, 0, and z should always start with 0, equals 0 squared, plus c is 0, equals 0. This is a recursive function. Let's call it again. Z is now 0. F, c is 0, z is the output of the last iteration, is 0, squared plus 0 equals 0 again. As we can see, this goes on and on and on. So, the absolute value of z never grows bigger than 2. So point 0 can be considered part of the Mandelbrot set. Let's try another point. Right here in the center of this little circle. This is -1. That gives us f, c is -1. Z should always start with 0. 0 squared minus 1 equals -1. That gives us f of -1 equals -1 squared, which is 1, minus 1 gives us 0. That gives us f of -1. Z has become 0. I can see where this is going. 0 squared minus 1 gives us -1 again. Also for c is -1. This goes on and on and on. Let's get a point we know is not part of the Mandelbrot. For example, here at 1. That gives us f1. Z should start with 0. Squared plus c is 1 gives us 1. C is 1. 1 is the output of the last function. So that gives us z is 1 squared is 1 plus 1 gives us 1 plus 1 is 2. Let's continue. f1 equals 2 squared plus 1 gives us 5. After recursively iterating this function 3 times, z, the absolute value of z, has grown bigger than 2, so 1 is not part of the Mandelbrot set. Let's try to implement this in Clojure. I have already defined a function, recursions, that takes a complex number, c, and decides the shade of red that point makes on a 2D map. Here. It is less red for a lesser value and more red for a bigger value. So, let's start off by defining the Mandelbrot function. Let's call it Mandelbrot. It takes 2 arguments, namely c and z, and returns the square root of z plus c. It's that simple. It's amazing to see how such a simple function can give rise to such a complex cosmos. Let's continue on with the recursions function. It is a recursive function, so let's use a loop where z should always start with 0. And as you saw with, for example, c is 0 or c is -1, the recursion went on and on and on. We want to prevent that, so we keep track of the number of iterations and stop the recursion after a predefined maximum, here defined in max iterations, has been reached. Let's call the Mandelbrot function and store its return value in R for return Mandelbrot. It takes two arguments, namely C and Z, and this recursion should quit under two circumstances, one being that the maximum number of iterations has been reached, the other one being, the other one being that the absolute value of the return value of the Mandelbrot function has grown bigger than 2. So the return value of Mandelbrot has grown bigger than 2. In either one of these cases, the function should return the number of iterations, so it can decide the color of red that is shown in the 2D grid. So we return the number of iterations. If neither of these conditions are met, we should continue the recursion, where Z has become the output of the last Mandelbrot function, here stored in R, and we have to increase the number of iterations. And this completes our recursions function. Okay, so let's test it. As we saw, for C is 0, the recursion never stopped. It went on and on and on. 0, 0, 0, 0. So, if we call the recursions function with C is 0 and give a maximum number of recursions, for example 5, it should return that maximum number of recursions, 5. And it does. We saw the same behavior for another point that is within the Mandelbrot set, -1. It went from -1 to 0 to -1 to 0 forever. So, if we call that function with a maximum number of recursions of 5, it should also return 5. We tested a point that was not part of the Mandelbrot set, 1. And even after 2 recursions, the absolute value of Z had grown bigger than 2. So, if we call recursions with point C is 1 and a maximum iterations of, who cares, 5, it should return 2. And it does. That completes our recursions function. Except that it does not, because we conveniently only used the real axis and ignored that the Mandelbrot set uses the entire complex plane. So what we have to do is adapt our Mandelbrot and recursions function to be able to handle complex numbers. We mainly have to adapt the sum, the product, and the absolute value to be able to handle complex numbers. So let's do that. Let's clear that all away. Adding two complex numbers is easy. If we have, for example, 3 plus, let's say, 2y, and we want to add to that 4 plus 1i, we cannot add apples to oranges, so we take apples to apples, the real parts plus the real parts, and then we take the oranges, the imaginary parts, plus the imaginary parts, which becomes 3 plus 4 is 7, plus 2i plus 1i. If I have 2 oranges and I add 1 orange, I get 3 oranges. That is 3y. So, the answer to 3 plus 2i plus 4 plus 1i becomes 7 plus 3i. We want to make a Clojure function of that, so let's replace all of this with variables. Let's say that the 3, the first part, the real part of the first number we want to add is, let's say, x, a, and the imaginary part is y, a, imaginary. plus x b plus y b I. And this becomes apples to apples xa plus xb plus yai plus ybi. So let's do that in Clojure. Define complex summation, and let's define a complex number to be a tuple of its real part and its imaginary part. X, y, a, I, and x, b, and y, b, I becomes an imaginary number where the real parts are added together and the imaginary parts are also added together. That is all for the complex summation. Taking the product of a complex number is a bit more involved, but not by much. So let's get rid of this and that. And now, if we want to, for example, add the complex numbers 3 plus 2i with 4 plus 1i, we can use a little bit of algebra to rearrange this by taking the real part of the first number times the second number and the imaginary part of the first number with the second number, which gives us 3 times 4 plus 1i plus 2i times 4 plus 1i. And the last step, to get rid of the brackets, we take this part times this part plus this part times the imaginary part, and for the second number, this part times the real part times the imaginary part, which gives us 3 times 4 plus 3 times 1i plus 2i times 4 is the same as 4 times 2i plus 2i times 1i, 2i times 1i. As you can see, this got rid of the brackets and we can simplify this a bit further. 2 times I times 1 times I, it's all multiplication. We can rearrange this however we like. For example, we can do 2 times 1 times I, and I times I equals to I squared, which equals to minus 1. This gives us 2 times 1 times minus 1, which gives us minus 2. So this part has become minus 2. And here we have 3 times 4, which equals to 12. Now, let's first add the real numbers. Again, we cannot add apples to oranges, so we first take the real parts of these numbers, which are these, add them together, and then we take the imaginary parts of this formula and add those together. 3 times 4 is 12. 12 minus 2 becomes 10. And that gives us 3 times 1i plus 4 times 2i. If I have 4 of 2 oranges, I have 8 oranges. So that gives us 3 times 1 orange plus 8 times 1 orange, where orange is of course the imaginary part, And if I have 3 of one orange and 8 of one orange, that gives me 11 oranges. So this becomes 11y, which gives us 10 plus 11y. I'm sorry. Which is the answer to this product. To implement it in Clojure, let's substitute the numbers with variables again. And remember, we just need the square of z, not a product. So that gives us x plus yi times x plus yi times itself. That makes it a bit easier. So let's take the real part of the first times the second and the imaginary part of the first times the second, which gives us x times x plus yi plus yi times x plus yi. Let's get rid of the brackets. This times this, and this times this, plus this times this, plus this times this, which becomes x times x, x times x, plus x times yi, plus x times yi, plus yi times x is the same as x times yi, plus yi times yi, x times x becomes x squared, and yi is the same as y squared times I squared. I squared is minus 1, so that becomes y squared times minus 1, which becomes minus y squared. Okay, so again, let's add the real parts together, x squared and minus y squared, and then add the imaginary parts together. So that gives us x squared minus y squared plus x y I times x y I is x y I times 2. And this is the complete formula to take the product of an imaginary number. So let's again implement this in Clojure. The square of a complex number, here defined by x in the real part and y in the imaginary part, becomes the square of x minus y squared, and for the imaginary part, x times y times 2. Okay, let's continue with the absolute value. The absolute value of a number, for example here on the real plane 1, is its distance from 0. So the distance from 0 to 1 is 1. The absolute value of 1 is 1. Same goes for minus 1. The distance from 0 to minus 1 is also 1. The absolute value of minus 1 is 1. And on the complex plane, it is the same. For example, 1 minus 1i here. The absolute value of that number is its distance from 0. We can calculate that by viewing this as a triangle. And if we define the distance in the real part as x and the distance in the imaginary part as y, we simply get the Pythagoras function x squared plus y squared to calculate the absolute size of this complex number. So let's implement that in Clojure. absolute size of a complex number, here defined by x and y, as the square root of x squared plus y squared. And this gives us all the functions we need. So let's start replacing them. Plus should now become z plus. Z times z will replace with our square function. The 0 here should be a complex number now, which is 0 in the real part and 0 in the imaginary part. And lastly, let's replace the ABS function with our newly defined complex absolute size of r. Okay, that's it. Let's test it. To keep things more to the point, I predefined the drawing and zooming functions in Clojurescript. You can check out my GitLab for that. And here it is, our fully working Mandelbrot. I can zoom in by clicking. Just to show you, it is possible to change the maximum number of iterations, so you get a less performant but more detailed view of the Mandelbrot. And in a later episode, we will use shaders to re-implement the Mandelbrot drawing function to have a more performant edition. This is quite slow, but for today, that's it. Thank you for watching and goodbye.